Fundamental interactions, also known as fundamental forces or interactive forces, are modeled in physics as patterns of relations in physical systems, evolving over time, whose objects appear not to be reducible to more basic entities. There are four conventionally accepted fundamental interactions: gravitational, electromagnetic, strong nuclear, and weak nuclear, each understood as the dynamics of a field. The gravitational force is modeled as a continuous classical field. Each of the other three is modeled as a discrete quantum field, and exhibits a measurable unit or elementary particle. Gravitation and electromagnetism act over potentially infinite distances across the universe and mediate everyday phenomena of human experience. The other two fields act over minuscule, subatomic distances. Synthesizing chemical elements via nuclear fusion within stars and quasars, the strong binds the atomic nucleus the force released during nuclear fission as in detonation of a nuclear bomb whereas the weak mediates radioactive decay. Modest gravitational effects are conventionally predicted via refinements of the theory of universal gravitation. Yet the gravitational phenomenon itself is conventionally explained as a consequence of space-time's dynamic geometry curving in the vicinity of mass, and is modeled by the general theory of relativity. UG and G are comprised classical mechanics. As energy alters spatial and temporal relations effects notable at vast energy levels such relativistic effects on space and time are modeled in relativistic mechanics, whose relativity theory extends classical mechanics via GR and special theory of relativity. Experimentally detected phenomena of elementary particles were first modeled in quantum mechanics. For predictive accuracy at high energy, however, QM was set to SR, and yielded quantum field theory, whose first quantized the electromagnetic field, quantum electrodynamics. QED was reduced along with the weak field to the QFT Electroweak theory. The strong field was modeled as quantum chromodynamics. EWT together with QCD and the Higgs mechanism which models the phenomena of some particles bearing mass comprise particle physics standard model. Theoretical physicists working beyond the standard model seek to quantize the gravitational field toward predictions that particle physicists can experimentally confirm, thus yielding acceptance of a theory of quantum gravity. Other theorists seek to unite the electroweak and strong fields within a grand unified theory. Yet all four fundamental interactions are widely thought to align at an extremely minuscule scale, although particle accelerators cannot produce the massive energy levels to experimentally probe at the Planck scale to experimentally confirm such theories. Still, some theories, principally string theory, seek both QG and GUT within one framework, unifying all four fundamental interactions along with mass production within a theory of everything. General relativity. In his 1687 theory, Newton postulated space as an infinite and unalterable physical structure existing before, within, and around all objects while their states and relations unfold at a constant pace everywhere, thus absolute space and time. Inferring that all objects bearing mass approach at a constant rate, but collide by impact proportional to their masses, Newton inferred that matter exhibits an attractive force. His law of universal gravitation mathematically stated it to span the entire universe instantly, or, if not actually a force, to be instant interaction among all objects. As conventionally interpreted, Newton's theory of motion modeled a central force without a communicating medium. Newton's thus theory violated the first principle of mechanical philosophy, as stated by Descartes, no action at a distance. Conversely, during the 1820s, when explaining magnetism, Michael Faraday inferred a field filing space and transmitting that force. Faraday conjectured that ultimately, all forces unified into one. In the early 1870s, James Clerk Maxwell unified electricity and magnetism as effects of an electromagnetic field whose third consequence was light, traveling at constant speed in a vacuum. The electromagnetic field theory contradicted predictions of Newton's theory of motion, unless physical states of the luminiferous ether are presumed to fill all space whether within matter or in a vacuum and to manifest the electromagnetic field were aligning all phenomena and thereby holding valid the Newtonian principle relativity or invariance. Disfavoring hypotheses at unobservables, Einstein discarded the ether, and aligned electrodynamics with relativity by denying absolute space and time, and stating relative space and time. The two phenomena altered in the vicinity of an object measured into be motion length contraction and time dilation for the object experienced to be in relative motion Einstein's principle special relativity, published in 1905. Accepted as theory 2, special relativity rendered Newton's theory of motion apparently untenable, especially since Newtonian physics postulated an object's mass to be constant. A consequence of special relativity is mass being a variant form of energy, condensed into an object. By the equivalence principle, published by Einstein in 1907, gravitation is indistinguishable from acceleration, perhaps two phenomena sharing a mechanism. That year, Hermann Minkowski modeled special relativity to a unification of space and time, 4D spacetime. So stretching the three spatial dimensions onto the single dimension of time's arrow, Einstein arrived at general theory of relativity in 1915. Einstein interpreted space as a substance, Einstein ether, whose physical properties receive motion from an object and transmit it to other objects while modulating events unfolding. Equivalent to energy, mass contracts space, which dilates to mere events unfold more slowly establishing local tension. The object relieves it in the likeness of a free fall at light speed along the pathway of least resistance, as straight lines equivalent on the curved surface of 4D spacetime, a pathway termed worldline. Einstein abolished action at a distance by theorizing a gravitational field 4D spacetime that waves while transmitting motion across the universe at light speed. All objects always travel at light speed in 4D spacetime. At zero relative speed, an object is observed to travel none through space, but age most rapidly. That is, an object at relative rest in 3D space exhibits its constant energy to an observer by exhibiting top speed along 1D time flow. Conversely, at highest relative speed, an object traverses 3D space at light speed, yet is ageless, none of its constant energy available to internal motion as flow along 1D time. Whereas Newtonian inertia is an idealized case of an object either keeping rest or holding constant velocity by hypothetical existence in a universe otherwise devoid of matter, Einsteinian inertia is indistinguishable from an object experiencing no acceleration by existing in a gravitational field possibly full of matter distributed uniformly. Conversely, even massless energy manifests gravitation which is acceleration on local objects by curving the surface of 4D spacetime. Physicists renounced belief that motion must be mediated by a force. Standard model, the electromagnetic, strong, and weak interactions associate with elementary particles, whose behaviors are modeled in quantum mechanics. For predictive success with QM's probabilistic outcomes, particle physics conventionally models QM events across a field set to special relativity, altogether relativistic quantum field theory. Force particles, called gauge bosons force carriers or messenger particles of underlying fields interact with matter particles, called fermions. Everyday matter is atoms, composed of three fermion types, up quarks and down quarks constituting, as well as electrons orbiting, the atom's nucleus. Atoms interact, form molecules, and manifest further properties through electromagnetic interactions among their electrons absorbing and emitting photons, the electromagnetic field's force carrier, which if unimpeded traverse potentially infinite distance. Electromagnetism's QFT is quantum electrodynamics. The electromagnetic interaction was modeled with the weak interaction, whose force carriers are W and Z bosons, traversing minuscule distance, in Electroweak theory. Electroweak interaction would operate at such high temperatures as soon after the presumed Big Bang, but, as the early universe cooled, split into electromagnetic and weak interactions. The strong interaction, whose force carrier is the gluon, traversing minuscule distance among quarks, is modeled in quantum chromodynamics. EWT, QCD, and the Higgs mechanism, whereby the Higgs field manifests Higgs bosons that interact with some quantum particles and thereby endow those particles with mass, comprise particle physics standard model. Predictions are usually made using calculational approximation methods, although such perturbation theory is inadequate to model some experimental observations. Still, physicists widely accept the standard model as science's most experimentally confirmed theory. Beyond the standard model, some theorists work to unite the electroweak and strong interactions within a grand unified theory. Some attempts at GUTS hypothesize shadow particles, such that every known matter particle associates with an undiscovered force particle, and vice versa, altogether supersymmetry. Other theorists seek to quantize the gravitational field by modeling behavior of its hypothetical force carrier, the graviton, and achieve quantum gravity. One approach to QG is loop quantum gravity. Still other theorists seek both QG and GUT within one framework, reducing all four fundamental interactions to a theory of everything. The most prevalent aim at is string theory, although to model matter particles, it added SUSY to force partis Lisa Euro, and so, strictly speaking, became superstring theory. Multiple, seemingly disparate superstring theories were unified on a backbone, M-theory. Theories beyond the standard model remain highly speculative, lacking great experimental support. Overview of the fundamental interaction. In the conceptual model of fundamental interactions, matter consists of fermions, which carry properties called charges and spin A plus or minus 1 or 2. They attract or repel each other by exchanging bosons. The interaction of any pair of fermions in perturbation theory can then be modeled thus: two fermions go in a interaction by boson exchange, or two changed fermions go out. The exchange of bosons always carries energy and momentum between the fermions, thereby changing their speed and direction. The exchange may also transport a charge between the fermions, changing the charges of the fermions in the process. Since bosons carry one unit of angular momentum, the fermions' spin direction will flip from +1 or 2 to a 1 or 2 during such an exchange. Because an interaction results in fermions attracting and repelling each other, an older term for interaction is force. According to the present understanding, there are four fundamental interactions or forces: gravitation, electromagnetism, the weak interaction, and the strong interaction. Their magnitude and behavior vary greatly, as described in the table below. Modern physics attempts to explain every observed physical phenomenon by these fundamental interactions. Moreover, reducing the number of different interaction types is seen as desirable. Two cases in point are the unification of electric and magnetic force into electromagnetism. The electromagnetic interaction and the weak interaction into the electroweak interaction. See below. Both magnitude and range, as given in the table, are meaningful only within a rather complex theoretical framework. It should also be noted that the table below lists properties of a conceptual scheme that is still the subject of ongoing research. The modern quantum mechanical view of the fundamental forces other than gravity is that particles of matter do not directly interact with each other, but rather carry a charge, and exchange virtual particles, which are the interaction carriers or force mediators. For example, photons mediate the interaction of electric charges, and gluons mediate the interaction of color charges. The interactions, gravitation. Gravitation is by far the weakest of the four interactions. The weakness of gravity can easily be demonstrated by suspending a pin using a simple magnet. The magnet is able to hold the pin against the gravitational pull of the entire Earth. Yet gravitation is very important for macroscopic objects and over macroscopic distances for the following reasons. Gravitation is the only interaction that acts on all particles having mass. Has an infinite range, like electromagnetism, but unlike strong and weak interaction. Cannot be absorbed, transformed, or shielded against. Always attracts and never repels. Even though electromagnetism is far stronger than gravitation, electrostatic attraction is not relevant for large celestial bodies, such as planets, stars, and galaxies, simply because such bodies contain equal numbers of protons and electrons and so have a net electric charge of zero. Nothing cancels gravity, since it is only attractive, unlike electric forces which can be attractive or repulsive. On the other hand, all objects having mass are subject to the gravitational force, which only attracts. Therefore, only gravitation matters on the large-scale structure of the universe. The long range of gravitation makes it responsible for such large-scale phenomena as the structure of galaxies, black holes, and it retards the expansion of the universe. Gravitation also explains astronomical phenomena on more modest scales, such as planetary orbits, as well as everyday experience, objects fall. Heavy objects act as if they were glued to the ground. And animals can only jump so high. Gravitation was the first interaction to be described mathematically. In ancient times, Aristotle hypothesized that objects of different masses fall at different rates. During the scientific revolution, Galileo Galilei experimentally determined that this was not the case, neglecting the friction due to air resistance and buoyancy forces. If an atmosphere is present, all objects accelerate toward the Earth at the same rate. Isaac Newton's law of universal gravitation was a good approximation of the behavior of gravitation. Our present-day understanding of gravitation stems from Albert Einstein's general theory of relativity of 1915, a more accurate description of gravitation in terms of the geometry of space-time. Merging general relativity and quantum mechanics into a more general theory of quantum gravity is an area of active research. It is hypothesized that gravitation is mediated by a massless spin-2 particle called the graviton. Although general relativity has been experimentally confirmed on all but the smallest scales, there are rival theories of gravitation. Those taken seriously by the physics community all reduce to general relativity in some limit, and the focus of observational work is to establish limitations on what deviations from general relativity are possible. Electroweak interaction. Electromagnetism and weak interaction appear to be very different at everyday low energies. They can be modeled using two different theories. However, above unification energy, on the order of 100 GeV, they would merge into a single electroweak force. Electroweak theory is very important for modern cosmology, particularly on how the universe evolved. This is because shortly after the Big Bang, the temperature was approximately above 1015 K. Electromagnetic force and weak force were merged into a combined electroweak force. For contributions to the unification of the weakened electromagnetic interaction between elementary particles, Abdus-Salam, Sheldon Glashow and Steven Weinberg were awarded the Nobel Prize in Physics in 1979. Electromagnetism. Electromagnetism is the force that acts between electrically charged particles. This phenomenon includes the electrostatic force acting between charged particles at rest, and the combined effect of electric and magnetic forces acting between charged particles moving relative to each other. Electromagnetism is infinite-ranged like gravity, but vastly stronger, and therefore describes a number of macroscopic phenomena of everyday experience such as friction, rainbows, lightning, and all human-made devices using electric current, such as television, lasers, and computers. Electromagnetism fundamentally determines all macroscopic, and many atomic level, properties of the chemical elements, including all chemical bonding. In a 4 kg jug of water there are of total electron charge. Thus, if we place two such jugs a meter apart, the electrons in one of the jugs repel those in the other jug with a force of. This is larger than what the planet Earth would weigh if weighed on another Earth. The atomic nuclei in one jug also repel those in the other with the same force. However, these repulsive forces are cancelled by the attraction of the electrons in jug A with the nuclei in jug B and the attraction of the nuclei in jug A with the electrons in jug B, resulting in no net force. Electromagnetic forces are tremendously stronger than gravity but cancel out so that for large bodies gravity dominates. Electrical and magnetic phenomena have been observed since ancient times, but it was only in the 19th century that it was discovered that electricity and magnetism are two aspects of the same fundamental interaction. By 1864, Maxwell's equations had rigorously quantified this unified interaction. Maxwell's theory, restated using vector calculus, is the classical theory of electromagnetism, suitable for most technological purposes. The constant speed of light in a vacuum can be derived from Maxwell's equations, which are consistent with the theory of special relativity. Einstein's 1905 theory of special relativity, however, which flows from the observation that the speed of light is constant no matter how fast the observer is moving, showed that the theoretical result implied by Maxwell's equations has profound implications far beyond electromagnetism on the very nature of time and space. In other work that departed from classical electromagnetism, Einstein also explained the photoelectric effect by hypothesizing that light was transmitted in quanta, which we now call photons. Starting around 1927, Paul Dirac combined quantum mechanics with the relativistic theory of electromagnetism. Further work in the 1940s, by Richard Feynman, Freeman Dyson, Julian Schwinger, and Shinichiro Tomonaga, completed this theory, which is now called quantum electrodynamics, the revised theory of electromagnetism. Quantum electrodynamics and quantum mechanics provide a theoretical basis for electromagnetic behavior such as quantum tunneling, in which a certain percentage of electrically charged particles move in ways that would be impossible under classical electromagnetic theory, that is necessary for everyday electronic devices such as transistors to function. Weak interaction. The weak interaction or weak nuclear force is responsible for some nuclear phenomena such as beta decay. Electromagnetism and the weak force are now understood to be two aspects of a unified electroweak interaction. This discovery was the first step toward the unified theory known as the Standard Model. In the theory of the electroweak interaction, the carriers of the weak force are the massive gauge bosons called the W and Z bosons. The weak interaction is the only known interaction which does not conserve parity. It is left-right asymmetric. The weak interaction even violates CP symmetry but does conserve CPT. Strong interaction. The strong interaction, or strong nuclear force, is the most complicated interaction, mainly because of the way it varies with distance. At distances greater than 10 femtometers, the strong force is practically unobservable. Moreover, it holds only inside the atomic nucleus. After the nucleus was discovered in 1908, it was clear that a new force was needed to overcome the electrostatic repulsion, a manifestation of electromagnetism, of the positively charged protons. Otherwise the nucleus could not exist. Moreover, the force had to be strong enough to squeeze the protons into a volume that is 10 or 15 of that of the entire atom. From the short range of this force, Hideki Yukawa predicted that it was associated with a massive particle, whose mass is approximately 100 MeV. The 1947 discovery of the pion ushered in the modern era of particle physics. Hundreds of hadrons were discovered from the 1940s to 1960s, and an extremely complicated theory of hadrons as strongly interacting particles was developed. Most notably, the pions were understood to be oscillations of vacuum condensates. John Sakurai proposed the ρ and omega vector bosons to be force-carrying particles for approximate symmetries of isospin and hypercharge. Geoffrey Chew, Edward K. Burdett and Stephen Fortune grouped the heavier hadrons into families that could be understood as vibrational and rotational excitations of strings. While each of these approaches offered deep insights, no approach led directly to a fundamental theory. Murray Gell-Mann along with George Zweig first proposed fractionally charged quarks in 1961. Throughout the 1960s, different authors considered theories similar to the modern fundamental theory of quantum chromodynamics as simple models for the interactions of quarks. The first to hypothesize the gluons of QCD were Muyang Han and Yoichiro Nambu, who introduced the quark color charge and hypothesized that it might be associated with a force-carrying field. At that time, however, it was difficult to see how such a model could permanently confine quarks. Han and Nambu also assigned each quark color an integer electrical charge, so that the quarks were fractionally charged only on average, and they did not expect the quarks in their model to be permanently confined. In 1971, Murray Gell-Mann and Harold Fritzsch proposed that the Han-Nambu color gauge field was the correct theory of the short-distance interactions of fractionally charged quarks. A little later, David Gross, Frank Wilcock, and David Politzer discovered that this theory had the property of asymptotic freedom, allowing them to make contact with experimental evidence. They concluded that QCD was the complete theory of the strong interactions, correct at all distance scales. The discovery of asymptotic freedom led most physicists to accept QCD, since it became clear that even the long-distance properties of the strong interactions could be consistent with experiment, if the quarks are permanently confined. Assuming that quarks are confined, Mikhail Shifman, Arkady Weinstein, and Valentin Zakharov were able to compute the properties of many low-lying hadrons directly from QCD, with only a few extra parameters to describe the vacuum. In 1980, Kenneth G. Wilson published computer calculations based on the first principles of QCD, establishing, to a level of confidence tantamount to certainty, that QCD will confine quarks. Since then, QCD has been the established theory of the strong interactions. QCD is a theory of fractionally charged quarks interacting by means of 8 photon-like particles called gluons. The gluons interact with each other, not just with the quarks, and at long distances the lines of force collimate into strings. In this way, the mathematical theory of QCD not only explains how quarks interact over short distances, but also the string-like behavior, discovered by Chu and Forchi, which they manifest over longer distances. Beyond the Standard Model. Numerous theoretical efforts have been made to systematize the existing 4 fundamental interactions on the model of Electroweak unification. Grand unified theories are proposals to show that all of the fundamental interactions, other than gravity, arise from a single interaction with symmetries that break down at low energy levels. GUTs predict relationships among constants of nature that are unrelated in the SM. GUTs also predict gauge coupling unification for the relative strengths of the electromagnetic, weak, and strong forces, a prediction verified at the LEP in 1991 for supersymmetric theories. Theories of everything, which integrate GUTs with a quantum gravity theory, face a greater barrier, because no quantum gravity theories, which include string theory, loop quantum gravity, and twistor theory, have secured wide acceptance. Some theories look for a graviton to complete the Standard Model list of force-carrying particles, while others, like loop quantum gravity, emphasize the possibility that time-space itself may have a quantum aspect to it. Some theories beyond the Standard Model include a hypothetical fifth force, and the search for such a force is an ongoing line of experimental research in physics. In supersymmetric theories, there are particles that acquire their masses only through supersymmetry breaking effects, and these particles, known as moduli, can mediate new forces. Another reason to look for new forces is the recent discovery that the expansion of the universe is accelerating, giving rise to a need to explain a non-zero cosmological constant, and possibly to other modifications of general relativity. Fifth forces have also been suggested to explain phenomena such as CP violations, dark matter, and dark flow. See also: Standard Model, Strong Interaction, Electroweak Interaction, Weak Interaction, Gravity, Quantum Gravity, String Theory, Theory of Everything. Grand Unified Theory, Gauge Coupling Unification, Unified Field Theory. Quintessence, a hypothesized fifth force. People: Isaac Newton, James Clerk Maxwell, Albert Einstein, Richard Feynman, Sheldon Glashow, Abdus Salam, Steven Weinberg, Gerard T. Hooft, David Gross, Edward Witten, Howard Georgi. References, Notes. Bibliography, General, Davis, Paul, The Forces of Nature, Cambridge University. Presser 2nd ed. Feynman, Richard, The Character of Physical Law, MIT Press, ISBN A0-262-56003-8. Shum, Bruce A., Deep Down Things, Johns Hopkins University Press. While all interactions are discussed, discussion is especially thorough on the weak. Weinberg, Stephen, The First 3 Minutes, A Modern View of the Origin of the Universe, Basic Books, ISBN A0-465-02437-8. Weinberg, Stephen, Dreams of a Final Theory, Basic Books, ISBN A0-679-74408-8. Texts, Padme Narbhan, T. After the First 3 Minutes, The Story of Our Universe, Cambridge University Press. ISBN A0-521-62972-1. Perkins, Donald H., Introduction to High-Energy Physics, Cambridge University Press. ISBN A0-521-62196-8. Riazuddin. Non-Standard Interactions. NCP 5th Particle Physics Synthesis 1, 1 €25. Retrieved March 19, 2011 A.